Good afternoon, everyone. We're going to go ahead and pick up where we left off today in class. We ended talking about systems, so we just want to reiterate a couple of things. Unfortunately, I don't have my writing tablet, so I cannot write on screen. So just try to remember and tie it back to what we discussed yesterday. If you need to pause it, please go ahead and do so. But we want to sort of lead you on the path to understanding how we use our understanding of thermodynamics and thermochemistry to understand what's going on in terms of overall reactions. Now, I have three types of systems that we deal with: open, closed, and isolated. An open system is just that, open to the environment. So that means matter can go in and out, or energy can also be transferred in and out. A way that we can consider this is any reaction that we've done so far this year. We didn't put any lid on it before we began. We didn't cover it in any type of foam, anything like that. So it was open. If the temperature changed, you could easily feel it. A closed system would be similar to an open system in that energy can go in and out, but it's also taking a look at the fact that energy can still go in and out, but matter is stuck inside. Okay? So if I have a gas produced, it will be trapped inside of this container. The last type of system that we deal with is called an isolated system. Now, why is it isolated? Well, we have a lid on it, so that keeps any type of matter inside. But we also keep energy out. So if I'm sitting, I have a reaction that's going on, and the room is really, really hot, and the temperature would affect it. Because I have it in an isolated system, the reaction can go on as it normally would proceed. That means any heat generated would stay inside, and any extra heat given off would remain. So let's keep moving. When we do our actual reactions, this is preparing you for how you're going to proceed with your project, we use what's called a calorimeter. It's very, very simple in terms of what we're going to do, but you can see it's just a styrofoam cup. We have our water with whatever substance dissolved in it, so that could be a chemical reaction. It could be just us taking the time to dissolve something, and a thermometer. And we're measuring what happens as a project goes on. So imagine, and of course I'm not going to do this, I have some ethanol, and I was to figure out a way to light it to determine how much energy is going to be given off by that reaction. Everything will be able to stay in because, again, I'm not going to lose anything to the environment. This way it's going to be blocked. And usually I would find some kind of way to even cover it so I don't lose anything over the top. All right. Now, why do we use an isolated system for the process? Well, exactly as I said, I want to know specifically how much I'm going to need for that reaction or for that process. If I have an open or closed system, any energy that's evolved or comes off of that reaction, or any energy that goes into that reaction, would then change my data and give me the wrong result. So if I'm paying attention to this, what will we count as the system? What are the surroundings? Well, the system is going to be whatever the reaction is that's happening inside of the container. So in this case, it will be the water and the stuff that's dissolved in the water, because these are the things that are going to affect the overall process and the amount of heat that I get. The surroundings is then going to be everything else. That includes the thermometer, that includes the cup, that includes the table, anything that interacts or interferes with our overall process. Now, the next question asks me, sorry, that's my wife in the background. Where does the energy come from if the temperature increases? Now, because the only things that are inside are whatever I've dissolved and the water, that means that the energy that's released had to come from inside of the material. So this is when I break bonds and things come apart. Many times energy is released, and we talked about that with bond dissociation energy. Now, if the temperature happens to go down, then the question has to be asked going the opposite way. Where does it go if it decreases? That may mean that we're actually forming new bonds. If we're forming new bonds, that energy is going to be stored up. Overall, we're just looking at whether the energy is going to be absorbed by the system or whether it's given off by the system. Now, when we describe heat change, we usually do it in terms of a couple of different units. The first one, the main one that we're going to use, is called the joule. This is the SI unit. This is the one that's used around the world. The second one, which is used more so in the United States, is the calorie. Of course, substituted as or abbreviated as lowercase CAL. This is the amount of energy that's required to raise the temperature of 1 gram of water 1 degree Celsius. Now, from that, because this is more of an American system instead of metric, we can take and convert it into joules to utilize it. Now, to make a quick distinction, we also have the calorie, notice capital C, capital CAL. These are dietary calories. Now, one of these capital C calories is equal to 1,000 actual scientific calories. So when you look at it and it says it has 150 calories, multiply that by 1,000. That's really going to be what you're dealing with. Now, heat in general, we know that it's going to flow from high to low temperatures to eventually equal out or hit what we call a thermal equilibrium. Temperature is just that measurement of the heat that's been transferred and in the particles at that time. Next thing we're going to deal with is called the specific heat capacity. Now, this is the book definition, the amount of energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. If you remember our short little demonstration that we did on Monday, where we took our hand, we put it on the desk, we took the other hand, put it on the leg of the chair of the table. A lot of people noted that, hey, okay, the table leg seems like it's colder. Initially, it might seem like it's colder, but then it warms up very quickly. Well, why does it warm up? Well, it's a metal, so it requires less energy to be transferred in to raise the temperature versus the table, the slate, or whatever stone material that is, requires a lot more energy to heat up. This is why I can sit a hot beaker on there and touch and move it and touch it a few seconds later without burning my hand completely. But if I did that with metal, most metals, it would still be relatively hot. Now, we use this understanding of the specific heat capacity to try to figure out the heat that's been transferred in or out of a system. And this is the formula we're going to use. It's Q equals M times Cp, which is our specific heat, times the change in temperature. Now, delta T meaning the change. So that means we're going to do the final temperature minus the initial temperature. So where the temperature stops minus where it started. Now, this is very, very important because if I'm decreasing my temperature, that means I'm going to have a negative delta T. That's giving me the opportunity to realize that that energy is being released. If it's a positive value, then that means that energy was absorbed, and we can classify it as such. Let's look at a couple of quick things, labeling each part. Again, Q is our energy or heat, usually going to be expressed in joules. M is our mass, given in grams. Specific heat, joules per gram Celsius, because again, it's the amount of energy per gram in degrees Celsius. And last, this is the change in temperature. This is a table, this is a table of specific heat values to sort of give you an idea of what we mean. Those that are towards the bottom here, like lead, it doesn't take much to get the temperature to change. Also note that, hey, we have all of these metals that are down here towards the bottom. As we go up, we have ethanol as a gas, ethanol as a liquid. Note that there's a difference between it. It's all dealing with how the energy is transferred, with the highest one being water. Now, this is going to have a lot to do with the density of water, but also it's going to have a lot to do with the hydrogen bonding that's taking place. The energy is going to sort of be transferred around as things move. Let's look at a couple of examples of how to calculate this. 45-gram sample of iron is heated from 25 to 50 degrees. How much energy is required? Notice that the specific heat of iron is given at 0.449 joules per gram Celsius. Well, let's plug it in. Trying to find Q, M is 45, C is 0.449, and delta T is 50 minus the 25, so 25 degrees Celsius. Now all I'm going to do is plug it in and solve for the one that I'm missing. My grams cancel as well as my unit for a Celsius. I'm left with joules, which is what I wanted in the first place. After multiplying the values, I end up with 505.125 joules. 505 joules will be my final answer. So, in order to take a 45-gram sample of iron and raise the temperature from room temperature 25 degrees Celsius to 50 degrees Celsius, I have to put in 505 joules of energy. Let's look at another example. What is the specific heat for an object if 12.5 gram sample is heated from 12 degrees Celsius to 28 degrees Celsius using 100 joules? Notice I have to do some rearranging here because I'm given Q in this case. Q is 100 joules. M is 12.5. Trying to find C. And again, they give me the delta T. So I started off at 12, ended at 28. So 28 minus 12 gives me 16. This is my base formula. I have to rearrange it to solve for my specific heat. When I do that, I'm going to divide both sides by M and delta T. So now all I have to do is plug in my values. Once I've done that, that's going to allow me to keep joules, grams, and Celsius. There's nothing to cancel them out. After dividing 100 divided by 12.5 times 16, I get 0.5. Sorry, technical difficulties. There we go. Now, when we look at this, we probably want to have some terms that'll help us to understand whether energy is going into the system or out of the system. We did this example in class, so we get a chance to move past it. But the main terms we're going to use is endothermic or exothermic. We know that that base thermic is telling us we're dealing with heat. So we need to focus on the endo versus exo part. Now, when something is endothermic, that's looking at a system absorbing energy from the surroundings. So, in my mind, endo, think inside. If I'm thinking exothermic, this is where I'm looking at a system that is giving off, like most bugs, a lot of bugs have exoskeletons. Or when I'm leaving the room, I exit the room. So it's being given off. Now, if I have something that's endothermic, this is going to feel cold to the touch. Now, in your head, you're saying, well, how is it going to feel cold if it's absorbing energy? Well, it's going to absorb energy from everything. That includes my hand. So, as it's pulling energy from my hand feels colder. When I'm dealing with something that is exothermic, that's where energy is going to be given off. So it should feel warm or hot to the touch. This is going to be because, again, the energy from the system is being given off to everything in the surroundings. That includes my hands. So it should feel warm to my hands if it's exothermic. If it's endothermic, it's going to feel cooler to the touch. Now, this leads me to understand, or try to understand, a simple term, enthalpy. Now, enthalpy is going to be the heat content of the system. What do you mean? Well, when I have a reaction or a process that takes place, that energy released or absorbed would be my enthalpy. Because of the fact that I cannot measure the enthalpy of a substance as it sits, I have to do it based on the change. It's usually going to be represented by the letter H. And I know you're saying there's an H here, but it doesn't start with H. Why are we using H? Good question. I'd ask a lot of other chemistry teachers. Sorry. Now, since we measure the change, again, before and after. This allows us to see whether we went up in energy or down in energy. In the example of what we're looking at, well, I have here A plus B yields C plus D. Notice that this is my beginning, this is my final. My final is less or has less energy than my beginning. Therefore, this is exothermic. Delta H would be negative. Okay? So negative delta H, exothermic. Now, if I'm looking here, my initial versus my final here, notice that my final state is higher than my initial state or my starting point. Because of that, I have more energy at the end than I started with. I had to absorb energy, positive delta H. Okay, so positive value, meaning I had to put energy in to start the process, positive delta H, endothermic. If I'm seeing that I ended up with less energy, that means once the reaction started, I was releasing energy, releasing. It is exothermic. All right. Now, this is the point I'm going to leave you at for now. We now have to take this and try to put it in context with our overall project. Make sure you finish your notes. I will see you all in class. Have a wonderful day.